One of the confounding parts about practicing engineering is that the input values that we have for our real world problems to solve don't turn out to be nice integers or nice even numbers or things like that. And that's why many of these homework problems that you're assigned end up giving you some practice in that. In other words, the given information doesn't exactly line up with the tabulated property values that are tabulated in the thermodynamic properties for phase change type substances and other type of tabular thermodynamic property tables. And so the idea of interpolation the idea of interpolation is a skill that you really are going to have to master and quickly as you start working through your homework problems. And the reason is that is not that we're trying to be mean in assigning problems that have nice even numbers associated with them, but because when you begin practicing engineering, that's going to be your daily experience. So let's get started on some basic notes and basic guides, tips on how to interpolate in this class and beyond. And interpolation is going to be required throughout the rest of your mechanical engineering undergraduate career. So being good at interpolation is going to pay off now and for future classes as well. Well, let's start off with an easy thermodynamics problem for H2O water. What's the boiling point of water when the pressure is 300 kPa? Now, off the top of your head, you're pretty good. You could say, I know the boiling point at 100 kPa, but what if you've got a piston and cylinder and the pressure inside that piston and cylinder containing water is 300 kPa? What would the boiling point be there? Well, you say, wait a minute, I got this thing nailed. I'm going to go to the pressure table. I'm going to go down to, let's see, 3 bar, right? I'm going to change 300 kPa to 3 bar. I'm going to look down at 3 bar. I'll look at the saturation temperature, write that number down, and I got my homework problem solved. So let's do that. We'll start with a sketch to kind of look to remind ourselves where are we on the PV diagram. That's a kind of a good idea. And so we're at 300 kPa, and here's a sort of an isotherm that corresponds to 300 kPa. So what we're trying to find is this temperature right here, and we're going to call that T sub G, TG for 300 kPa or 3 bar. Okay, so simple as this. Here we are at our pressure table for H2O. We drop down and find 3 bar and 133.6. We write it down on our paper and we are done. Next problem. So easy. Okay, now is another problem, but it's similar, but it's a little bit harder. For H2O, what's the boiling point temperature at a pressure of 325 kPa? Well, that's going to be 3.25 bar, isn't it? And so we go to our pressure table. 3.25 bar is not tabulated, but I do see 3, and I see 3.5. And I know that 3.25 is halfway between 300 and 350, or 325 is halfway between 300 and 350. And so look, I don't have to write any formulas. I can do this with a calculator. All I got to do is enter these two numbers and take the average of those two numbers. So our boiling point temperature is halfway between those two numbers, and we use our calculator to find out that it is 136.25 degrees C. So we write that number down, we're done. That's easy, right? So we kind of did this by eye. Now we're going to do one that's harder. So I wouldn't exactly call this hard. I didn't label it hard. And it's fairly easy once you know the secret. So here's the rest of this video is to solve this problem. For H2O, what is the boiling point temperature at a pressure of 409 kPa, or in other words, 4.09 bar? And now, so I find 4 and I find 4.5. I'm 4.09. So I know that the boiling point temperature is between 143.6 and 147.9. Okay, got it. It's some number in between there, but I'm going to have to sharpen my pencil to figure this out. Okay, so let's go through the process, the procedure by which you're going to figure this out. It's called linear interpolation. So okay. And so do you see that what I do, I changed my font. I changed this to kind of a font to kind of make it look like you're writing this by hand on a piece of pencil and with pencil and paper. And here's what you should write down. I'd say just about all times. I was going to say until you get really familiar with this, but I would say always do this. I always had to write this down. A little, just make a little table on my homework solution. Left column, it's what I pressures. I've written down my two tabulated values, and I put my value in the middle of those. Okay, so I wrote those down. Then I copied off what I'm looking for, the saturation temperature. I wrote those two numbers down, 143.6, 147.9. All right. And so there's two ways to approach this thing. One is to blindly use a formula that I will disclose to you in the next couple of slides, or try to figure it out on your own to say, well, wait a minute, let's look at this left column and let's call this difference Z. Do you see it's 9? The difference at Z is 9. Okay. That's the distance or difference between these two numbers. What's the difference between these two numbers? I'm going to call it Z total. Well, that's 50. 50. Okay. And so do you see that there's a proportion here? Z over Z total is 9 over 50. 9 over 50. So that's like a proportion, isn't it? So the next thing I observe is that I'm trying to use some common sense. Say, look, TG is going to be at least 143.6. It can't possibly be 147.9. Okay. Unless P is 450. But anyway, do you see that it's going to be some proportion? It's going to be at least 143.6 plus some proportion of this difference here. And that proportion is Z over Z total. That is the nature of a linear interpolation. So you're going to start with this value and add a proportional amount in that proportion to this difference. And so I've labeled this question mark. So question mark equals at least this amount plus the proportion, the pressure proportion. That's going to be 9 over 50 times the difference in these two numbers, 147.9 minus 143.6. Okay, so I've got that written down, and I turned the crank on the calculator, and it is 144.37. And so to write out the result of the boiling point temperature, TG, at a pressure of 409 kPa is 144.37 degrees C. That is the essence of linear interpolation for a specific problem. Okay. Let's generalize, right? So let's see if you can, maybe come up with something to generalize, because I know a lot of folks, they might like to write down a formula. Okay, I got that. I can respect that. Okay, so let's go back then. Now we're going to back up. Instead of doing specific numbers, it's going to be sort of the same idea. I'm going to have two columns, X and Y. Y is my unknown. Y is unknown. Y1 and Y2 are known out of my tables, right? X, all three of these are known. X1 out of my table, X2 out of my table, and X, well, that was 409. That's my desired, I want Y at a desired X, okay? And so it's a repeat. I just copied and pasted text boxes from my previous one, okay? And so I've got Y is equal to, it's at least Y1 plus this proportion, sort of this this Z over Z total proportion, X minus X1 divided by X2 minus X1. And then here's my Y difference, Y2 minus Y1. So do you see the similarity? This is my X proportion is Z over Z total. And so, if you pause this video, you might scratch this down. Of course, you're welcome to do this, but this could be considered a little more formal example of a linear interpolation for any two variables. But I'm trying to set it up sort of the way you copy and paste numbers out of a thermodynamic property table. Okay. Well, this is I'm trying to throw at you several options that you may choose to select or not select. This is some of my handwritten work from, I think, 2020, before COVID hit, trying to show students how to linearly interpolate. And so it's the same type of, it's handwritten, but the same approach, with little different variables than the previous slide. Okay. Look, Dr. von Spakovsky has offered a superb one-page Microsoft Word document that is just an excellent mathematical treatment of linear interpolation. And so this also is very nicely done. If you're in Dr. von Spakovsky's class or if you swing by his office, I'm sure he will gladly share with you this one-page Microsoft Word document that also scopes out how to interpolate. Okay, if you need a little more video and some more examples, I believe I've included some more examples on how to interpolate in my video. Let's see, I'm trying to see how long it runs. Darn it, I didn't write down how long it runs, but anyway, under thermodynamics fundamentals, there's a video called How to Interpolate, and that could give you some additional ideas on interpolation, maybe some additional tricks of the trade. Okay, I now declare you an expert at interpolation. You say, oh, I'm a little nervous, and I can understand why. The trick is to practice, 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 and doing your homework problems gives you plenty of practice at linear interpolation, and you need to have that practice because you have to have that practice before quizzes and tests because you need to be able to interpolate fast. You can't get mired down and getting confused on interpolation. That will cost you too much work time in a timed environment. So practice, practice, practice to get good at interpolation. Just keeping up with your homework will give you all the practice you need to do well and perform well on quizzes and tests and the exam. So there are two approaches for interpolating. So one is my mental proportion approach. So if you write stuff down, scratch it down, doesn't have to be a work of art. On your solution, you can get to this mental proportioning approach very quickly on your calculator, or you can blindly use a formula, and that can work, but I don't recommend it. I like this mental proportion approach. It also shows that it shows your work. It helps to show your work so you can demonstrate to the person grading your work, whether it's a quiz or a test, that you really see what you're doing. And if you have the smallest type of mathematical blunder, that person reviewing your work can give you the partial credit that you deserve. And so that's my recommendation. Now, I see what's coming up next is gases and equations of state. So be prepared for the next video in this sequence. We're going to totally switch gears. And so be aware of that. So all the previous Chapter 3 videos have involved phase change substances like H2O, refrigerant, propane, things that can change phase as an engineer. The next video is going to introduce you to things that we commonly recognize as gases. Let's see, gases, air, nitrogen, carbon dioxide at ambient conditions, argon, things like that we recognize as gases. We're going to have some different approaches for determining property, quantifying properties. So do be aware of that. So far we've covered phase change substances, PV diagrams, stuff like that. Then now we're moving on to gases, and we're not going to be drawing vapor domes. There won't be any vapor domes for gases. So just be aware of that, and join me next time where we talk about equations of state for gases and how to evaluate properties for gases like air.